So good afternoon, everyone. Today we are pleased to welcome Dr. George Helffrich from Earth Life Science Institute of Tokyo Institute of Technology to give us a seminar on planetary accretion and core formation from a thermodynamic perspective. George received his PhD on geological science from Northwestern University in 1990. After that, he continued his research career as a postdoc researcher in Carnegie Institute of Washington for about 2 years. Then he moved to University of Bristol and became a professor of geophysics in 2004. Then in 2014, he moved to his current institute, the Earth Life Sciences Institute of Tokyo Institute of Technology, as a principal investigator until now. So George's research focused on the physical and the chemical process in the interior of a planet, for example, core formation, core mantle interaction, and also lithosphere, asthenosphere, boundary, etc. So today he will talk about the chemical behavior of metal and silicate in planetary interior during planet formation, in particular in the early Earth and Mercury. So now let us welcome George. George, please.
Hello, everyone. Thanks for joining me at the talk, and thanks for inviting me to give it. This is the first Zoom colloquium that I've given, so the experience for me is rather strange, not being able to see an audience and interact with an audience like I usually do. But I'll try to muddle along, and we can adapt. Now, I really hope there's some way that people can ask questions or interrupt me in the middle of the talk if I'm unclear about something. But since I don't know how to operate Zoom properly, and I don't know what etiquette is for that kind of interaction, you're going to have to take the initiative on your own to do this if there's any way of doing it. So please, I encourage you to stop me, however it can be possible. If I'm going too fast, or if I haven't explained something very clearly. Okay. Let's see. Okay, so I'll just start along here. Start in. Just to give you a preview of what I'm going to be talking about, here is a picture. Whoops. No, that's not a picture. This is a mistake. This is also a mistake. Let me try to get my pointer up here. This is a picture of a stony iron meteorite, which exemplifies the two major components of of the materials that build a rocky planet. First of all, there's the metal part of the stony iron meteorite, and then there's the rocky part, or the stony part, which is these transparent things, which are crystals of olivine, common mineral on the surface of the Earth that are embedded in the metal. And what these meteorites represent are fragments of some disaggregated planet that was found as a meteorite after it fell to the Earth. So they're records of different stages of planetary formation in the process of accretion. The other thing that I'm going to be talking about, let's see here, whoops, I have to do it that way, okay. The other thing I'm going to be talking about is Mercury, because Mercury, if you look at this, if you look at this diagram, which shows Mercury's metal and rock or silicate abundances as compared to other planets and types of meteorites, you can see that it's heavily skewed. In the case of Mercury, there's much more metal than there would be if you look at any other composite solar system object. So the whole process of planetary accretion can actually help you gain some insight on what might be peculiar about Mercury's balance of metal and silicate. So that's the other topic that I hope to be able to touch on in this talk. Can everyone understand me and hear me? Is there any possibility of any interaction here?
Yeah,
Can-
we can hear you. And I think
Okay.
if the audience have any questions, just feel free to interrupt George and ask questions anytime you want. Yeah.
Yes, thank you very much. Okay, so what I'm going to start off at the beginning is try to give you a geologist's perspective on this whole process, because to you as astronomers, and it might seem a little peculiar. So I'm going to talk about some comparisons between an astronomical approach and a geological approach to this problem of planetary accretion and how you might model it. So I am a geologist by training, so so just to remind you, and geology uses present day or knowledge of present day processes and rock samples to infer conditions about the past. So there is an analogy between this to what astronomers do, which they use knowledge of physics to interpret observations to infer conditions at great distances and further into the past as you go out and further and further from the Earth. But both disciplines attempt to surmount these barriers of time and space by using a combination of data that you have and a combination of knowledge of the physical processes that give you insight on how these actually work to make the universe that we look at today. So here's an example of data from a geologist's viewpoint. Okay, so we have rock samples that might be terrestrial, lunar, meteorites, etc. You have cometary materials and interplanetary dust. All these things are something that geologists can analyze. Geologists have experiments how rock forming elements behave under controlled chemical conditions. And then there's a theory, which the one that I use most often is thermodynamics. And there's thermodynamic data, which describes the physical and chemical properties of chemically reacting materials. In contrast, astronomers have star and exoplanet and galaxy observations. They also have dynamical observations of those objects to the scale of solar system all the way through galaxies. And then they have knowledge of the periodic table and the table of nuclides, which actually gives them an idea of how nucleosynthesis works and what the distribution of elements are in the universe. The kind of knowledge that we work with, again, they're analogous. They're analogous things that analogous disciplines that we work in. We have knowledge of physics, physical chemistry, thermodynamic, continuum mechanics for deformation of materials, and fluid dynamics also of deformation and distribution of materials during geological processes and accretion processes. And astronomy has more exotic disciplines that feed into it, like particle physics, quantum mechanics, and to some extent signal processing to actually get the information that astronomers use to infer what's going on elsewhere in the universe. So let's look at the geologist mindset now that we've kind of compared and contrasted my idea, at least, of how astronomers and geologists think about things. I mean, geologists are basically what we find ores, okay, for society to do something useful with. And the useful things they do nowadays is they make iPhones, or they make Fiat 500s or trains or something like this that benefits society's workings. Geologists, sorry, yeah.
Sorry to interrupt. I'm just wondering whether because in sometimes in the bottom column it shows the pointer options of your for your pointer option. So I wonder whether you can actually remove that.
If I can, I don't know.
Yeah, maybe it's because when you use the pointer,
if I do it, I can't use the pointer anymore.
Yeah, well, I think
so that's the only way that I can actually see the pointer.
Okay, I see. Yeah, never mind.
Okay, sorry about that. Yeah, I don't seem to be able to make the pointer come otherwise. So I'm sorry for the distraction. Uh-oh, now I'm getting lost here. Uh-oh,
Yeah, don't worry, take your time.
here I am. Okay.
Yeah.
So we're back here talking about materials. So geologists also know, because it's their job, how much of each element makes up the planet. Something that you can infer from this, from tables of elemental abundance, like this thing shows over here, is that on average, the Earth's density is about 2 times more than rock at the surface. And you know the Earth's average density from actually its orbital characteristics around the sun. You can figure out the mass, and from the size of the Earth, and its mean density. And the mean density is actually a lot more than rock is at the surface. So the conclusion is that this extra material that makes up the extra mass of the planet is probably in the Earth's core. You can put this thing on a more quantitative basis or visual basis by looking at a diagram like this. Now, this is a relatively interesting diagram, so I'll talk about it for a minute here. What's shown on the diagram is one spot for most of the elements that make up the Earth. So that's what you see, a collection of spots, and they're plotted here on this x-axis in terms of their condensation temperature, such that if these elements were turned into a gas, this is the temperature at which the gas would condense into something solid. Okay, so things that are at the right-hand side over here are relatively refractory because they condense to a solid at a high temperature. Things that are down here are relatively volatile because they condense to a solid at a low temperature. Okay, so that's how these things are plotted, just based on their condensation temperature. And the y-axis of this is the abundance of the element in the silicate part of the Earth, part that we stand on, related to their abundance in C1 chondrites. All right, and these elements these element ratios are normalized such that magnesium is 1. So here's magnesium, and this is the value 1 that goes across here. Okay, so what you see is that elements that you think of as being constituent part of rocks, like silicon, magnesium, calcium, etc., are pretty much in chondritic relative proportions right here, because they're all clustered around 1. But there are other elements down here which are gold, palladium, ruthenium, platinum, rubidium, iridium, rhenium, osmium, that are very much depleted, almost by a factor of 1,000, compared to what you expect to see them in chondrites here. So this is telling you that there's been elemental segregation during the formation of the Earth that put a lot of these elements in with the rest of the other elements that these like to alloy which is iron. So these elements are depleted because they're sequestered in the core of the Earth. All right. So these ones are in the rocky part of the Earth, and these ones are missing because they're in the metallic part of the Earth, or the part of that stony iron meteorite that we saw that was actually bright and shiny as opposed to transparent. And now another aspect of this geological way of thinking about planetary accretion is the idea of a magma ocean. And you have a cartoon of it, on the left side of this diagram. And just to emphasize, this is simply a practical model for capturing the complex behavior of a system, but it has the advantage that it can be geochemically calibrated, and I'll explain what that means in a couple of slides here. But in this diagram on the right, there is an assumption that this thing that's called a magma ocean exists in a homeostasis between the impactors, the material that's falling into a planet as it grows, the atmosphere that's actually produced by the hot material that's forming the planet, and the growing planet itself. So this represents some kind of steady state condition as new material is being added to a planet as it accretes. Okay. Now to give you a little more detail, to talk you through some more details on this. Okay, so this is now the blow up of the diagram that we saw in the previous thing. And you have impactors which come in from the outside, which melt in this magma ocean, which is this part right here. And the dense part of them, which is the metallic part, actually drops to the bottom of it. Okay, so the metal part now, which is now in the bottom of this molten magma ocean, actually forms some kind of pond on the hard part. So this is the solid part that's underneath it at some rheological base of this magma ocean. And when the metal ponds, it accumulates and then dikes its way down to the center of the planet, because that's where the gravitational potential energy is lowest. And what this does is it forms a core, and then the metal there essentially pushes the silicate material out, or it floats on top of it, depending on how you might want to think of it. And so you get the planet growing this way and separating the metallic part down here with silicate part, which is up here. So this is the model that you have of this process. Now let me explain what I mean, how this model can be geochemically calibrated. Okay, here's this diagram that we saw a few slides ago again. And I want to focus you on these elements that are circled right here, which are cobalt and nickel. Okay, so these are two elements that like to alloy with iron, so they're called siderophile. But unlike these elements, like gold and platinum down here, which are highly siderophile, these are only moderately siderophile. Okay, so they sit in, they're depleted, but not depleted as much as these are. But they like to alloy with iron. Now notice here that both cobalt and nickel have about the same abundance in the silicate earth relative to chondrites right here. Okay, they have about the same thing observationally on the earth. Now this is sort of a key feature here. Now what you can do is you can do experiments in apparatus that look like these two devices that you see on your screen here. Can I get my pointer back? Nope. Here it comes. So this is a diamond anvil cell in which the sample is squeezed between the faces of two diamonds at very high pressure. And then because the diamonds are transparent, you can shine a laser through them. They heat the sample up, and you can produce temperatures which are very similar to the interior of the Earth, all the way to the center of the Earth. But the sample size is very small. You can only get about 0.2 millimeters of material inside this thing to be able to squeeze it and heat it up that high, heat it up to high temperatures. On the other hand, here's this apparatus, which is about the size of a tram, I guess you could call it. That's about as tall as a tram. And then these are very heavy presses, hydraulic rams that are used for shaping metal, actually, in factories, but geologists use them to do experiments by putting a capsule in between the opposite side of these rams. And the good thing about it is that the samples that you can do experiments on are much bigger than the diamond anvil cell. They're about 2 millimeters in size. But unfortunately, you can't go up to very high pressures, only about 30 GPa, which is about halfway to or about a third of the way actually to the core mantle boundary in the Earth. So this is not very high pressure, but it's still high pressure from the point of view of a geologist. From experiments done in these apparatus, you can get information about how these elements like nickel and cobalt behave when they are melted in the presence of metal and rock. Okay, so what this diagram shows you over here is what's called the partition coefficient, which is the concentration of the element in the metal versus the concentration of the element in the silicate. And it shows you that at 0 pressure here, so at room pressure, if you're a metallurgist and you see what the concentration of cobalt is in metal relative to rock, there is about 80 times more cobalt in metal than there is in rock at room pressure. That's what this line shows you. Up here for nickel, there is about 400 times more nickel in metal as there is in rock. Okay, so that's what these diagrams, this shows you. And you know this from experiments. Now, as you increase the pressure of this experiment now, what you see is that cobalt, the partition coefficient of cobalt gets lower. That is, it wants to, more of it wants to be in rock as opposed to metal. But nickel also does the same thing. So what you see is that these two lines meet at a pressure that's about 25 or 26 GPa. And at that point, they achieve the concentrations that you see in the Earth. Okay, so let's move on to this diagram again here. Sorry, back to this diagram. And what now you see is that by invoking high pressures of equilibration, then you can make those two concentrations agree with one another, with what you see on the Earth. So the inference of this is that, and the geochemical calculation comes about, is that you can, from experiments like this, you can say what the pressure of this metal pond that the silicate and the metal actually were in equilibrium with, because that's what you see in the silicate or in the rock that sits on the surface of the Earth today. So this gives us an idea of how high a pressure this process happened at, and therefore how deep the magma ocean on the growing planet actually was. Okay, so that's how this process is calibrated geochemically. So going back to this diagram now, we have this metal pond, which represents pressure. And if we're going to simulate the accretion of a planet, we get the pressure at the boundary between metal and the rest, and silicate, the rest of the planet here, by just the mass of the body as it's grown. Okay, from the mass, we can actually come up with a profile of gravity and density as a function of radius of the growing body, which I'll show you in a minute. And then from these experiments, we know that the magma ocean bottom pressure, which is this pressure right here, is, depending on the element that you look at, it's somewhere between 2/7 and 2/3 of the pressure of the core mantle boundary. So in other words, the magma ocean doesn't extend all the way through the planet. It just extends only to some intermediate depth which is given by this figure between about 2/7 and 2/3 of the pressure of the core mantle boundary. These come from experimental relations. Now the other, so now that we know that the whole planet isn't molten, then we have another constraint on how geologically things must be behaving. So what's shown on the right here are sets of experiments. Each of these spots is an experiment where chondritic material has been heated up at different pressures and different temperatures. And this thing shows the temperature of where the first solid occurs when material is cooled down to where it starts to freeze. Okay, that's called the liquidus. Over here, you have another set of experiments which show the solidus, which is where the first liquid appears when you're heating it up. Okay, so in between this line and this line, then there's a mixture of solid and liquid. It's not all solid and it's not all liquid. Underneath here, it's all solid. Up here, it's all liquid, but in between, it's solid and liquid. So what that tells you is that this idea of a magma ocean that has a bottom, which is this metal pond on this that you see in the diagram on the left here, actually must exist somewhere in this range between the liquidus and the solidus right there. Okay, so now this gives you what that range is as a function of pressure. And now we have all the elements that we need to actually build our planet, because we can take a generic idea of, oh, no, I don't, sorry, there we go. Where to go? Excuse me. So back to here now. So we have a generic rock and metal, and we can define a sort of generic solid, which I call a goo here, which has a density and a bulk modulus such that when you compress the material, then it forms then it compares favorably with the material of rock and metal that's given by the PREM model, which is a geophysical model of the structure of the Earth. Okay, so what this diagram shows is PREM values, which are the solid lines for gravity as a function of radius. So here's gravity in the core, becomes pretty much level from the core mantle boundary out to the surface of the planet to about 10 meters per second squared, which is gravitational acceleration. And then here's pressure, which is at its maximum at the center of the Earth, which goes down to 0 at the surface. So this is the solid line is the geophysical one. The dashed line is this generic rock and metal that makes up the planet. This part is the metallic part. This is the rocky part on the outer parts of the planet. And the virtue of this is that I don't really need to know what the rock and what the metal is particularly, but with just 4 parameters for each material, rock and metal, I can fully describe this curve. So it's a very simple way to parameterize the curve, but will also give me all of the interior properties that I need to do the simulation for a planet. Okay, so this is our goo that the planet is going to be made from. So any questions about this so far?
Hey, George.
Yeah.
I can go back to the slides before.
There?
Yeah. Yes.
Uh-huh.
So for prime, the solid line, I thought it also included the inner core. So there's a density jump between inner core and the outer core. So on this plot, I didn't see the jump of the prime pressure profile. So what does that mean here?
Okay. let me make one thing is that where at the core metal boundary, which is the line where the material turns from rock on this side to metal on this side, you see a jump. Well, not a jump, but a discontinuity. Okay.
No,
So
I mean the boundary between inner core and outer
Yeah.
core. That should also be a density jump for the prime density. So
Okay,
I didn't see here.
No, you don't see it because pressure, the only thing you're seeing here is pressure and gravity. Okay. And the pressure is continuous across the density jump.
Oh, okay, that makes sense.
All right. So there's not going to, the density is discontinuous, but the pressure is continuous. Okay. So that's why you don't see it on this diagram. So the only things you see on this are the big changes, which are the change from metal to rock. And you see not a first order discontinuity, but a second order discontinuity in the gravity and pressure field there.
Yeah, thanks.
Okay, any other questions?
Sorry, can you explain again what is the solid and dashed line? I don't quite understand here. The prime
Okay,
glue.
All right, the
Yes,
PREM is a geophysical, a collection of geophysical observations that give us the structure of the Earth. Okay.
geophysical.
And the solid lines are the pressure profile that PREM gives us and the gravity profile that PREM gives us. Essentially, PREM is a profile of density versus radius in the Earth. Now, that's empirical. It's observed. Now, what the dashed line is it's a simple model which contains 4 adjustable parameters that gives you the PREM pressure and gravity profile. Okay, and all it needs is 4 parameters for each of these 2 materials, rock and metal. Okay, so although PREM has about 500 pieces of data that go into it, this theory of this goo, which is rock and metal, each have only 4 parameters which go into it. So it's a very simple way to parameterize any kind of rocky material that you're going to build a planet from. Okay.
So which 4 parameters are you referring to actually?
So
the
4 parameters, no, these are the 4 parameters are a zero pressure density, a zero pressure bulk modulus, a pressure derivative of the bulk modulus, and a pressure derivative of the thermal expansivity. Those are the only 4 parameters that one needs to be able to do this.
Okay, yeah.
Okay.
Thanks.
Okay, so now the next thing I'm going on to is to talk about some chemical concepts that control the element partitioning between metal and silicate. Okay, so these are the things that are going to control what the surface of a planet actually looks like from the outside, or what ours looks like when we stand on it. So here's some chemical concepts which I'm going to introduce to you. So here's a chemical reaction. Okay, you have some metal which is just called M generically, and it's in the form of an oxide. And this metal has a chemical oxidation state of plus N. Okay, so the formula for this oxide is going to be MO, so it's bound with oxygen, and then N over 2 of them to actually balance charges. All right, so this is the oxidized form of the metal that's in the silicate. Now there's a reaction which is going to make it which is going to put M into the metal that you make the planet, and then it's going to produce oxygen as a byproduct. Okay, so this is an oxidation reduction reaction. So you have silicate, you have metal in the silicate over here. You have M in the metal that's over here. So this is just a generic element that we call M. Now here, this is a more realistic one. Here's iron. Okay, so here I can write a reaction where iron reacts with oxygen, and it makes FeO, which is a material called wustite by a geologist. Okay, iron oxide. So this is a balanced chemical reaction. Now, it turns out to be a little tedious to try to deal with chemical reactions when oxygen is involved because of the oxidation reduction potential that you have to take into account to describe the reaction fully. So what you do is a mathematical thing where you add these two reactions together, okay, and just algebraically. And when you do that, then oxygen is on one side of the equal sign, on the other side of the equal sign at the same time, so you can make them go away. And instead, I can combine these two reactions into this reaction, which is a single one, which describes this M that's in the silicate reacting with iron in the metal to put M, this generic element, in the metal, and then put iron in the silicate. Okay, so now this doesn't involve any exchange of oxygen. There's just an oxygen atom over here, which was in the silicate, and the oxygen atom over here is also in the silicate. Okay, so this is just moving M from the silicate to the metal and moving iron from the silicate into the metal this way. All right, so this turns out to be a very convenient way of dealing with these kind of element partitioning reactions when you simulate planetary accretion. Now, how do you actually use this effectively? So this is the scheme that follows. Suppose that these concentrations are at equilibrium at some pressure and temperature conditions. So how does a change in the pressure and temperature condition affect the concentrations? This is something that you want to know, because you want to know that as the planet grows, whether more of this metal might go into the core, or might it stay in the rocky part of the planet? Okay, that's the sort of question you want to address with these kinds of techniques. So in order to approach it, you use the concept of a K, which is an equilibrium constant for the reaction. So if this is our reaction, then you write the equilibrium constant like this, which you call it K. And then this has to do with the mole fractions of M in the metal and the mole fraction of FeO in the silicate and the mole fraction of the metal oxide in the silicate and the mole fraction of iron in the metal. Okay, so this K are things that you can physically relate to the molar fractions of these elements that are in the different materials. Now, to underlie this with a little bit of theory, we have the free energy. We use the Gibbs free energy to actually calculate these things. So here's the Gibbs free energy change of the reaction, which involves the enthalpy, the entropy of the reaction, and the temperature. And this is the work done by pressure against volume. So this is pressure volume work that's done. And you equate this to the activity of a material times the absolute temperature and the universal gas constant. That's what R is. Okay, which you can also rewrite as this way. So instead of writing the activity, I've just broken it down into a concentration part, which is X, which is this thing that's down here. and activity, what's called an activity coefficient part, which is this part that's right here. That's what these gamma things are. So you notice that this X part is the same as that equilibrium constant that we wrote before. And the only new thing is this, activity coefficient, which is over here, which has some complicated models that go into describing how these behave, particularly for metals. So let's go back to this equation right here. If you, oh, nuts, I'm sorry. I find it very difficult to navigate with my finger. Let's go back to where we were here. Okay. So at this point, we have an equation which has RT on it. And if I divide both sides of this by RT, then I have delta H over RT, T delta S over RT, V delta P over RT. Okay. Now let's go to, now we have, now with that equation, then we can simplify this as the logarithm of the KD is equal to a constant times something divided by T times something that's multiplied by pressure and divided by T, which is what you got from that previous equation I was trying to show you in a very clumsy way. But empirically, if you do experiments on partitioning of elements between metal and silicate, then it turns out that the experiments can be modeled or can be very accurately described by an equation which is as simple as this. Okay, 3 parameters with a temperature dependent part and a pressure dependent part. And you can see these connections with enthalpy and entropy by looking back at the previous slide. And C has to do with volume change of the reaction that I was talking about before. So to show you what some of these experiments, modeling experiments actually look like, this is a diagram that shows some experiments which have to do with the KD for an element. This is magnesium over here. And it's plotted in a somewhat peculiar way, which if you look at this axis here, it's actually reciprocal temperature because of the way that equation was shown. And here's real temperature, which is up here across the top. So this goes from 2500 K to about 6500 K. And these are, this is that KD expression that I showed you for magnesium, which is now in both metal and silicate that has been investigated experimentally. So this is a line that you get if you plot the results of a bunch of experiments on a diagram such as this. And from the coefficients of this line, then you can obtain the values A, B, and C, which you get to describe how the KD behaves as a function of pressure and temperature. And now this gives you a tool for building a planet, because you can take some kind of initial composition, which is a chondrite of your choice, Ci or ensitite chondrites or others that you think the Earth is made from. And you can define a metal fraction of it by weight and oxide amounts of elements that you want to do this partitioning between metal and silicate between. So silicon would be one, magnesium would be one, aluminum would be one, and iron would be one in this case. Okay, so I've just written these elements as in their oxide forms in the list here. So now, so for each of these elements, then you have a KD expression, which describes how silicon behaves partitioning in metal and silicate, magnesium, aluminum, iron, etc. Okay, so I'd have 4 different KD expressions, one for each of these elements. Now, if I want to simulate how to build a planet, then for each of n steps, which is 1/n of a planetary mass if you're doing this in a unsophisticated way, or one impact from an n-body simulation if you're doing this in a dynamically consistent way like you do at your institute. Then from this you use the properties of the goo, because you know the mass of the material, to determine a profile of gravity, pressure, and from that you get the pressure of the core metal boundary, the pressure at the bottom of the magma ocean, and from that diagram that I showed you of the solidus and liquidus temperature as a function of pressure, then you get the temperature as a function of pressure as well in your magma ocean. So at the base of your magma ocean, at the pressure and temperature that you now know from the mass and temperature of your planet, then you effectively solve a series of simultaneous equations for each of those KD expressions, which I showed you before, for the elements that you want to do with. And then you solve them using the KD until you get a consistent solution. And that tells you what the fraction of that element is that's in the metal and in the silicate part of the planet for that particular impact, that particular n step. Okay, so then you mix the material back in at the bottom line here. You mix that equilibrated material in, that small parcel, back in with the core metal and the rock. Okay, so now your core metal is evolving separately from the silicate material that's in the magma ocean, and you're adding new material at the next step as it comes into the magma ocean, and now undergoes partitioning against the whole a different set of pressure, temperature, and chemistry, compositional conditions as the planet grows. So now what one of these simulations looks like is a function of step. So this is a fraction of mass accreted to the planet. So this is starting off with 0, and this is going to a fully accreted, in this case, Earth, as a test. So here are silicon, another siderophile element called niobium. Here's manganese, vanadium, chromium. This is iron right here. This is tungsten, this is cobalt and nickel, like we saw. So these are the partition coefficients at essentially at room pressure. And as the pressure and temperature conditions of the planet change during accretion, then the concentrations of these in the silicate and the core metal actually change. And this is what's shown in the diagram like this. Now, when you know you've done a good job, if at the end of your simulations, then these numbers that you get for the concentration of silicon, niobium, vanadium, etc., actually match the concentrations that we see on the surface of the Earth. Okay, so that's how you know that your simulation is actually doing something reasonable instead of just something that's your own fantasy about how clever your model is. Now let's great. Now I'm going to have to speed up because we're getting near the end of time here. So let's think a little bit of what one of the consequences of this element partitioning is. What I'm showing you in this diagram is this is a diagram you may not be familiar with, but this is a compositional diagram on a triangle, okay, for 3 elements: iron, silicon, and oxygen. Okay, if you plot up here, it's all iron. If you plot down here, it's all oxygen. If you plot over here, it's all silicon. All right. So in this space, iron-rich things are on this side, silicon-rich things are over here, etc. Now the other thing that I want to point out is that these quantities are plotted by weight, which turns out to be useful for simulation points of view and for actually doing some chemical calculations. So down over here, this is silicon oxide, SiO2, right at the bottom of your screen. In up here, this is another compound that's relevant for forming core materials, which is a solid alloy of iron silicon. Here is FeO. This is pure iron. Now, suppose I have a liquid, which is in the interior of a planet, that's in the core of a planet, which is here at position X. Okay. So now suppose with some of that liquid, then I take away some silicon dioxide, which is down here. I'm going to, if I take that away from this diagram, I'm going to move whatever liquid remains off in this direction, because I've removed silicon and oxygen. And that means the composition of this now must evolve towards the iron direction. Right. So if I take silicon dioxide out of this diagram, then I'll make things more iron rich. So what in the context of a growing planet, that means that if I take silicon dioxide out of the core of a growing planet, then the remaining material is going to be more iron rich. So now go think back to this generic exchange reaction that we were talking about before, and think about M as being silicon. Okay, so here's silicon dioxide, here's iron, and here's iron oxide, and then here's silicon that's in the core metal. Now the question is, what does the solubility of silicon do as the planet evolves? Because if I put silicon into the metal at the bottom of the magma ocean, and that metal at the bottom of the magma ocean goes to the center of the planet, so it's going to get hotter and it's going to go to higher pressure on this diagram here. Is the solubility of that going to increase, or is it going to decrease? Okay, so if the solubility increases, it's going to stay in the metal as it goes down. If it decreases, then it's going to be precipitated from the metal and then come out of the core. So you can use this whole idea of the KD again, which is the expression that you have here, or the activity actually, which includes the KD, to understand the solubility of these materials in the core metals. So in this case, silicon. And if I just look at the mathematics of this thing, no matter what the activity is here, I can have isosolubility lines when these two parts of the expression are the same. So when this KD expression, which I showed you before, is equal to these concentrations plus these activity coefficients, which I haven't talked about because they're rather complicated.
Sorry, George, to interrupt
Yeah.
you. May I know how many slides do you have remaining?
I'm going slow. I'm going slow.
Yeah, because
So,
I think we still have like 5 minutes at most.
I understand. Yeah.
Sorry.
Okay. So I'll try to speed through this then. Thank you. So going back here, then what you can do from this calculation is come up with a isotherms of solubility of silicon dioxide in core metal. That's what these contours show, and you can come up with you can describe how the planet evolves and the Earth evolves and forms the inner core by losing SiO2 here and forming solid iron at the surface of the inner core. So at the in the inner core of the planet. So the implication of this is that as the planet accretes, silicon, in this case, can go into the core metal. It stays in the core until the planet cools down, and then the silicon comes back out of the core. So this tells you that the elements just don't make one-way trips into the core or the mantle of a planet. Okay, so to briefly go through this, we're going to look at Mercury now. Mercury is weird. I described to you why before. There's a couple of reasons why Mercury might be weird. It might be depleted in silicate because it's close to the sun. It might be stripped of silicate by impacts or being in impactors, and we're going to take a geological approach to look at this. This just confirms that there are planets, exoplanet surveys have showed that there are planets that are dominantly metal. This shows you an example of a exoplanet which is located right about here, which is called K2-141b, which is about 50% metal, but it's about 4 times bigger than the Earth. So it's a strange planet, but it just shows you that some planets that are that are dominantly metal can form close to stars. So this is one possibility for why Mercury might be have so much metal in it. Another one is this scenario that Benz and co-workers showed a long time ago in 1988 from scale particle hydrodynamical simulations, which showed an impactor. And the point of this diagram is to show that the metal part actually separates from the silicate part, so it's possible to filter out the silicate part and form a planet which is a residue which is dominantly metal, and that's something that Benz pointed out a long time ago. Further SPH simulations by Asfog and Royfer here more recently showed that Mercury could actually be an impactor because it shows a Mercury-sized impactor hitting a target, and then the impactor on the lower right turns out to be all dominantly metal. So another possibility might just simply be that Mercury was an impactor as opposed to a target. To take the chemical approach, then we can just ask if Mercury was stripped of silicate. Then we can assess this by looking at the surface concentration of sulfur on Mercury and look at the amount of metal that Mercury has in its core and ask whether the two could ever have been in equilibrium in the interior of a planet. Okay, so that's the approach that I'm going to take. The composition of Mercury is strange compared to the Earth. This is the Earth in showing the iron content and the sulfur content. There's almost no sulfur on Earth compared, and much more iron. Mercury has a lot more sulfur than it does iron, and this is chondritic abundances, which are much more rich in volatile elements. These are estimates of Mercury's core by Rivaldini and Van Hulst, and another higher estimate of the core composition, the amount of sulfur that's in Mercury's core, which we're going to look at here, which is about 5 weight percent approximately. In order to do this, you have to have some data, and this is a geological model which shows the partitioning. So this is sort of a KD expression right here for the amount of sulfur that's in both metal and silicate, which also takes into account the amount of nickel, carbon, silicon, oxygen, and sulfur that's in the metal and the silicate. So there's some tricks you have to, there's some deficiencies that you have to overcome to be able to apply this metal. I won't go into the details, but the results look something like this. I'm going to talk about this one diagram a little bit in detail, and then I'll stop. So what this diagram shows is a composition of sulfur that's in the core of Mercury. So this is 7 weight% sulfur in the core. Okay, we think we know what the surface of Mercury actually has on it, which is in the silicate, which is described by these lines right here. So it's between about 0.2 and 0.04 and 0.3 weight% silicate on, or FeO, on the surface of Mercury. And this is what the concentration of silica or of sulfur on the surface of the planet actually is. So we have sulfur at the surface, FeO at the surface. We have sulfur that's in the core. And then we can ask what planet would have all of those in equilibrium according to all of the KD expressions that we have. And what these contour lines show you are the pressure that's within the magma ocean that would have put those quantities in chemical equilibrium. And what you see from the labels on these lines is that the pressure for equilibrium is something on the order of 20 GPa to 45 GPa. And the pressure in Mercury right now is only 6 GPa. So what the conclusion of this is that Mercury must have been a much larger planet before it was disaggregated, stripped of its exterior, and turned into the Mercury that we see today. So that's another way to approach the question of what happened with Mercury. So in summary, the thermodynamical approach allows you to simulate the accretion of planets in a chemically consistent way, and there are certain types of problems that you can address from knowledge of the chemistry of the planet and the chemical conditions through which it evolved. So thanks for your time, and sorry to have been going along on this.
Yeah, no problem. Thank you very much for George to give us an interesting talk. So if you have any questions, you can raise your hand, or you can type in the chat room, or just unmute yourself to speak out your questions. So maybe I've one question first. You mentioned a situation about a return of silicate from the core to mantle. So it seems that there's some interaction between the core and mantle in this. I wonder whether this would also occur to other elements, and would that affect the isotopic chronology we derive for core formation? For example, hafnium tungsten chronology, would that affect it? Would this process of returning material from the core to mantle affect the isotopic dating for the core formation?
Well, yeah, it's so in answer to your question, yes, this happens with all elements, and yes, this happens with elements that are of particular interest to chronology of core formation, such as tungsten.
Yeah.
And the interesting thing is that tungsten has a couple of different oxidation states, and it can be sequestered into the metal, and it can also be teased into going back into the silicate if conditions, if the pressure and temperature conditions in the forming core change. So there is complications due of tungsten chronology for core formations that come about because tungsten can actually leave the core and go back into the mantle from when it was first formed.
I see, I see. Wow, then
I won't detail all those things here.
yeah, of course. Well, then that may create some problem when we use hafnium tungsten dating to date the core formation. Right.
Yeah, it requires more complex models that than have been really used up to now.
Okay. Well, that's okay. So I see some hands raised. So Dario, you can ask the questions.
How, George? Nice talk. I have a question about your equilibrium conditions of the metals between the core and the surface. You said you seem to use the surface as your benchmark. Is there an assumption that the surface composition today is the same as the composition of the bottom of the magma ocean that equilibrated with the core at the end of accretion? Because why would you want to compare to the surface and not to the the bottom of the mantle, for instance?
Well, I'm being a little bit loose with the term of the surface, just as because it represents the rocky part of the planet. And the only thing that we really have reliable samples from are the surface and the shallow part of the mantle through xenoliths that you get from volcanic eruptions that are very deep. So those are the only ones that these statements about what the surface of the Earth actually look like are made from. So those are the things that you're actually comparing to. If there's layers that are at the bottom of the planet, close to the core mantle boundary that we can't otherwise sample, then we don't know, we can't actually characterize them very well chemically. Okay. So does that answer your question, Dario?
Yeah, so that actually means that, there is this assumption, right? So it's not necessarily true that the composition of the surface is the one that actually equilibrated with the core.
Yeah, that it is an assumption. That's right, and you're relying on convection in the planet, in the silicate part of the planet, to homogenize it chemically.
Yeah.
But that is an assumption, and there are lines of evidence that are cited that say that the Earth hasn't been completely mixed that way.
Okay.
So Dario, is that you, Dario Alfe?
Yeah, that's me, George.
Well, welcome. I didn't expect to find you here.
So next we have, thank you. So next we have Fabian Snyder.
Yeah, thanks for the talk. That was very nice one. So my question is regarding the state of the metal pond in the planet. This is a transient state, right? So there's no reason to assume that exoplanets might have a consistent metal pond below their first layer of silicates, right?
Well, let's see. The model that one uses is of essentially a steady state process. Okay, that there's a balance between all of the incoming material and the outgoing radiation of energy, the formation of the atmosphere around and the formation of the atmosphere around the planet that serves to keep it essentially under similar conditions. But it's a model that tries to capture a dynamically very complicated situation, which, like you say, is transient because the body is growing all of the time as it does it. It's not steady state mass; it's steady state conditions. So so you have to realize the limitations of the model that you're using to simulate accretion. Does that help answer your question?
Yeah, thanks. Yeah, and also one, you've shown that the impactor actually can become the mercury after the collision. Do you know, does this also extrapolate to the high masses observed, for example, for K21 for 141b?
No, I don't know if there is any, because though that would come from the SPH simulations, which I'm not knowledgeable enough about to know the literature to say whether there's any restrictions on the size of the impacting bodies before new phenomena come into place that wouldn't allow the separation of metal and silicate.
Yeah, okay, thanks.
One problem of that, though, is that somehow if mercury or some other thing is an impactor, then somehow you have to capture it around the sun or around the central star, and dynamically that's a difficult problem. You have to be, it would be unusual to be able to do that. So preserving either Mercury or this large metal planet of 4.5 Earth masses around a central star would be difficult if it was an impactor in either case.
I see. So their history might be more complicated than. Okay. Yeah. Thanks a lot.